So as mentioned, I'm going to be giving you an overview of the topics from a more data science perspective. Let's get into it. Oh, can you see my screen okay?
Yeah.
Okay, great. So just as an overview, we're going to start with some statistics versus machine learning. What is the difference between descriptive versus inferential statistics and machine learning? Then we're going to go over some concepts that are important, things like optimization and how machine learning models learn over time. We'll do a brief overview of some models and then talk about some specific examples of papers relevant to medicine. Lastly, we'll talk a bit about data and how you should clean and prepare your data for use in machine learning, and then discuss some of the limitations of these approaches. Okay, what's happening? Sorry, I'm having some presentation issues. There we go. Okay, so in terms of a motivating example, the reason we want to use advanced statistics to study these kinds of systems is given right in front of you. So these data sets all have the same underlying two features in terms of their X and Y means, yet they're completely different spreads, and the way you would like to study them or understand them would be completely different. So the point of the slide is to say that basic statistics like means are not enough to describe the variation in data, and we want to use advanced features, in this case maybe standard deviation, but in other cases more higher order features to describe this, and that can be used as the basis for building machine learning models. Next. So just as an overview, descriptive statistics are high-level characteristics of data, things like the mean, standard deviation, and spread. These are important characteristics to understand your data. Yet when it comes to the ability to infer or guide decisions, that's where inferential statistics come in. These are statistical parameters that can be used to compute conclusions, predict future outcomes, and these are the basis of a lot of machine learning outcomes and machine learning workflows. Okay, so the common method in terms of what you're probably more familiar with would be something that uses descriptive or inferential analysis to understand the data in question. So for example, results from a blood test, results from a biobank of sorts, things like Pearson correlation, odds ratios, and p-values. These values could then be combined and analyzed further to develop a sort of system, a scoring system, a flowchart, something like this, which could then be used to evaluate and understand and score patients and direct them towards a particular treatment category. A common example of this that you might be familiar with in medicine is CHADS2-VASC, or the CHADS score. There are scoring categories for patients where they might be assigned a few points based on pre-existing conditions like hypertension, age, diabetes, etc. And based on the score they accumulate, they would be suggested for anticoagulation therapy or not. The important thing for something like this is you may notice that these are important and useful, clinically useful decision trees and decision frameworks, yet there's nothing magical about numbers like 1 and 2 and 0 that we use. We just use these because they're easy to compute and calculate in clinic. Now, what machine learning models allow you to do are to look at more complex relationships between these variables. For instance, maybe diabetes and hypertension might have an additive effect that would be more than just these two variables on their own, but a more simple decision framework model like this would not allow you to account for that, whereas machine learning might allow you to understand and express that relationship more readily within your data. Okay, so in terms of the machine learning workflow, we began with input variables. These vary depending on the type of model and type of situation that you're trying to train for. Once you have those input variables, you use a model to analyze the data, and this generates some form of prediction. The initial predictions are often never initially right. They tend to form off of randomly generated parameters, but that's perfectly okay, because the next step is to compare the predicted outcome to the actual outcome. So you may be trying to predict whether a patient would need coagulation therapy, and you'd compare the model's prediction of that outcome to what the clinician assigned to that patient. When this happens, you can use that error to adjust the weight of features that go into the model, and this will become more clear through an example. But the point is, these weights are continually evolving, and this training paradigm is what defines machine learning separate from inferential or descriptive statistics. The model improves as you expose it to more data over time. So once you have a finalized model with optimized parameters, these types of models are much smaller than the compute resources that might be needed to train machine learning models. And once you have these optimized systems, you can put them on smaller storages such as USB drives or on local computers where they can be used to analyze new patient data that the model has not previously seen and make predictions that can be clinically useful to direct the care for those patients. Okay, so just as a brief overview to give you an idea of what we've covered so far, machine learning starts with some form of input variables and it seeks to predict an output variable. So in the case of the atrial fibrillation example we used previously, a need for pharmacotherapy to manage coagulation. The model learns from training cycles over time. This is an important consideration for all machine learning models. The underlying pattern, and one important thing to highlight is that if the underlying pattern does not exist in data, there's no way for machine learning to develop one. It's not some form of magic where it can pull out relationships in data that wouldn't otherwise be obvious or exist. It's kind of the job of the people gathering the data to make sure that their data is high quality and actually presents the kinds of information necessary for a model to infer this. Now, there's some techniques we're going to talk about called feature engineering and feature extraction, where you can help kind of coerce non-obvious features and non-obvious versions information from your data out in a way that can help machine learning models develop on that. But it is important, I just want to highlight once again that these models cannot generate correlations or relationships in data that are not reflected underneath. And you should keep that in mind when you're gathering the data. Which data is a session that which model, sorry, is a session that Zoe's going to talk about more next week, and also Ricky the week after. We're going to give you a brief overview of a lot of different kinds of models to give you an understanding of how you might apply this in your own research. What data is the question I'll be answering today. So this is things like how do you clean and prepare your data for use in machine learning models. Okay, supervised versus unsupervised machine learning. So supervised machine learning paradigms are where models use input data to perform initial predictions. Now, crucially, what makes it supervised is that the model has the ability to compare its predictions with ground truth labels. So you know the outcome of the condition you're looking at, you know the correct assignment, and now training just becomes a process of comparing your initial prediction to a future prediction of the model. And over time, as the model is exposed to more and more examples, the difference between the predicted outcome and the actual ground truth outcome is minimized through the process of training. There are two large paradigms in supervised machine learning. There's regression. For example, with regression, you might be trying to predict a particular score or a continuous variable. A common example you might see in medicine-related papers are things like 10-year or 5-year survival rate for a patient. The second paradigm for supervised machine learning is classification tasks. So here you are seeking to put the outcome you're seeking to predict is a categorical variable. It might be something like, is this tumor benign or is this tumor malignant? You can do this based on the input data. And importantly, you have the ability to identify these relationships beforehand and train the models to looking at this. Unsupervised machine learning is a bit more complicated in the sense that it doesn't have these underlying class labels where you can say that this tumor is malignant or benign. Rather, the unsupervised models seek to learn underlying relationships and structure in data without knowing the examples or without knowing the correct class labels. And I believe we're going to do an example of k-means clustering today in our programming session. Okay, question break. Does anyone have any questions? Great. Okay, I'm going to jump forward. If you have any questions, me or Ricky are happy to answer, and we can keep going. Okay, so in terms of machine learning model types, just to highlight for you a few examples from papers that are on ArcSiv, which is a preprint server for kind of more engineering focused papers. There's a lot of really complex model architectures that you can see. I made this kind of bingo sheet as kind of a joke for you guys. There's like a lot of Bayesian or Lagrangian or Gaussian. Pick your mathematician here. Pick your machine learning neural network architecture here, and you can see papers have tons of combinations of these different ideas and different complex frameworks. But the important thing I want to highlight for you is that you don't need these kinds of complex approaches to develop real important clinically useful models that can direct decision. The models that I'll be showing you later on, the examples I'll be showing you later on are using simple regression-oriented techniques that predict based on features that are developed with medical insight or knowledge of patients, where people who can build these kinds of complicated models may not be able to provide that. Crucially, as medical students, you would be able to supply that medical expertise or that understanding of disease in a way that could develop simpler models that have higher predictive powers and sensitivity and specificity than something like these more complicated systems that don't have that biological understanding. Okay, so in terms of model types, linear regression is the main one we'll be talking about that you may be familiar with in the past. Logistic regression is another one you may have seen previously. Random forests, we talked about a bit in the first session. Essentially, if you've seen a decision tree, it's similar to a decision tree, except rather than one decision tree, it is an aggregation of hundreds of them. And rather than following the outcome of that individual, this collection of decision trees called a random forest is averaged or summed in some weighted way to predict the final result. The last class of machine learning models are neural networks. We're going to talk about these a lot more. I believe Zoe will do that session in a couple of weeks from now, just to give you an idea of the kinds of applications for these models. Okay, so in terms of linear regression is used to predict continuous variables only. So it's seeking to learn a relationship between your input variables and the output. So here we're looking to predict the days to stop smoking from the patient's weight. This linear function is fit based on its relationships between the variables. Now, you might be wondering, how does linear regression actually work? It's trained in a similar way to all the other machine learning models, where it arbitrarily draws a line or decision parameter, and then it seeks to optimize it over time by minimizing the error in the random initial position. So here it fits the equation. It's linear regression, so it's fitting a linear model with a weight and a bias. These two parameters together are called the parameters of the machine learning model, and these are what's optimized. The X is the input data that you are giving the model. In this case, it would be the patient's weight, and the Y is what you're seeking to predict. In this case, it'd be the days to stop smoking. Okay, so as I was saying before, how are parameters learned? W and B were the parameters we're talking about in linear regression models. They're learned through what's called optimization techniques. Now, these optimization techniques start with a random initial value, and over successive learning steps, they use mathematical algorithms like gradient descent or stochastic gradient descent or batch gradient descent. There are tons of others. The idea is to successfully use calculus to reduce the input of features that don't contribute to correct predictions and maximize the input of features that do contribute to correct conditions. And over time, your model would reach a minimum cost or at least make the minimum amount of errors through the use of this backpropagation algorithm to improve the weights of the contributing parameters. So here's a kind of a schematic of what linear regression looks like. You can see it starts with an initialization of the line at some arbitrary position. And over time, the distance of each of the points to the line is optimized. It's looking to minimize the distance of these points. And as you can see, the model will continue to train and continue to shift up over time to better fit the data. And this is a process of learning in machine learning models. Okay, yeah, quick question break if anyone has any. You can use the chat as well. That's also fine. All right, I'm going to jump forward. If you have any questions, feel free to drop them in the chat. Ricky can respond to you, and we can also read them out and talk. Okay, so in terms of the next feature we're going to talk a bit about machine learning pitfalls. So to the left, you'll see an example of what's called an adversarial attack. So this is a neural network-based system that is used to classify images. So as you can see, the left image is a panda, and all that's happened is that the researcher has added a random noise element to the image. And if you look to the right, it's now the same model that previously predicted panda is now predicting a gibbon, which this is what a gibbon actually looks like. So, maybe close, maybe not, I don't know, but it's just to say that these predictions are not very stable or not always very strong. So, when you hear about machine learning coming for radiologist jobs, the actual radiology images are quite noisy, and the ability to infer would have to be robust to this kinds of input of noise. So when we're talking about something that's doing a classification task for fun, like predicting pandas or gibbons or something, these standards for safety are a lot lower than would be needed in a clinical setting. The bottom example, you can see they're starting with an image of sloth, and they're adding the bare minimum amount of noise they need to make the model predict the race car class. As you can see here, to a human eye, this still looks like a sloth, but the machine learning model is tricked. So that is to say that the robustness of these machine learning models is still an open area of research and continues to be advanced, yet it needs to be thought about when you're developing models and thinking about how you can deploy them. The next thing we're going to talk about is overfitting. So the point of overfitting is to say you can force a correlation of a machine learning model with any data, but you don't want to go too far and actually predict the noise or sampling bias in your data, because that will make the model poor at generalizing and predicting data that it wasn't previously exposed to. And we'll talk about strategies to ensure that's not happening. So this is an underfit linear regression model. As you can see, there's a lot of error at various parts of the model. This would be a more optimized model, which fits the data really well. There's still some deviation or error within the function, but it's not so large that this model wouldn't be suitably predictive. Here you have the opposite side of the spectrum where the model is said to be overfitted. It's predicting every point within the data set, which with really good accuracy for the most part. The problem with this kind of approach is as soon as you expose this model to data it has not previously seen, it's likely to fail. And the reason is because there's just some variation in data that exists where we don't even want to be able to capture that with our model. And doing so means that if we're not exposed to the same data, we're more likely to make a mistake and be tricked by the noise that we've learned to interpret as a model rather than the underlying features and information that we're looking at. Okay, so next we're going to go over a bit of a motivating example. This is a paper published recently. It's talking about the selection of 51 predictors from 13,000, 14,000 candidate features used in machine learning models. And this machine learning model's goal was to improve coronary artery disease prediction. Okay, so one way to avoid overfitting and improve generalizability is through trained test splitting. As you can see in this paper, they split their initial cohort size of almost 200,000 people into a development set that they use to train the model and a holdout set. And this table shows the comparison of the features of the development and holdout sets. What it's trying to say is that these two groups are very comparable in most senses, meaning that a model that performs well in the development set should perform well in the holdout set as well. Yet the reason you want to do this is because you want to have data which your model has not previously been exposed to validate your model in the future. That's an important thing to avoid overfitting. The second important feature I want to highlight here is cross-validation. So rather than training the model once, they actually trained it 5 different times with using different components of data as the holdout set to test their models overall. Here they did it 5 times, so it's called 5-fold cross-validation. The benefits of this type of approach is that rather than training your model once and just happen to be getting lucky that your model predicted exceptionally well in both training and test sets, by doing it 5 times, you show that the architecture you developed and the features you input to your model are very robust and likely to lead to sustained predictive accuracy rather than something that's just a one-off that happened to happen as a more fluke sort of thing. Okay, so the next step I want to highlight is the removal of redundant features. Now, as I previously said, you want to minimize the amount of noise or poor information that goes into your machine learning model. There's a few reasons for this. First, you only want to learn correlations that are important enough predictive value. And secondly, is this general rule of thumb down here, the idea being that the number of data points you need is 10 times the number of features that you put into your model. So the less features that you try and put in, the less data you need, the easier it is to develop a model. The other thing is, as these sample sizes and feature spaces get really, really big, this training becomes even more computationally costly and takes a longer and longer time for people to actually be able to do, which makes it difficult to go through. So just to look at this from the beginning, they started with 12 demographic characteristics, and through the optimization of their machine learning model, they found that only 3 actually ended up being of high predictive value. So they removed everything else to remove the likelihood of overfitting. With lifestyle, they started with 11, cut it to 6, and you could see the features that they retained over here. Same thing with medical history. They actually cut a lot. They started with almost 8,000 and they end up with just 5, which just goes to show you that you don't, it's good to start with a high dimensional feature space, but once you actually come to training and deploying your model, as you can cut it down to make it more refined, it's more likely to generalize well and lead to inferences that are useful elsewhere. Surgical variables, they went from 5,000 to 0. And then family history, they went from 32 to 2, just looking at mainly the incidence of heart disease or the presence of heart disease in their family or for their father. Okay, so in terms of take homes from this example, to improve model generalizability, I think it's important to maximize dataset diversity to the greatest extent possible. For the example I used, it's a UK biobank dataset, which is notoriously quite high in populations of white ancestry. The problem is models trained on this type of dataset will generally perform poorly when they're trying to predict outside groups that were not included in their training set. So people of different ethnic backgrounds are unlikely to have these models perform well on them. This is true because there's a lot of underlying biological variation. And this is particularly true if you're using genetic data, where the reference genomes for the white population and, for example, the East Asian population are very different, and it becomes difficult to predict unless you have sufficiently representative data sets. Okay, second thing to say is to remove unnecessary features. You remember they started with 14,000 and they end up cutting it to about 50. This reduces the likelihood that you end up training and learning the noise features, and makes it more likely that you actually develop a good fit that's likely to be predictive outside of your training and test sets of data and to be generalizable and usable with real world data. They performed train test splitting, so they didn't report the accuracy of their model on the training data. They reported the accuracy of their model on previously held out data that their model had not seen before. The value of this is that, as I said previously, you're not learning the noise within the data, you're learning the actual relationships that can generalize, and the test set is a testament to the ability to generalize because the model's not seen it. They cross-validated the instances of training, meaning they trained 5 times as opposed to just once, because if you just train once, it's more likely that you just randomly pick the one that had the highest accuracy and reported on it, rather than showing that your model is robust and able to do this. Lastly, one thing that you may consider for your own machine learning projects is to resample to address class balance. So if you're trying to identify particularly rare conditions, like people who might have some sort of genetic variant or people who might have a very rare disease, if the data set not having sufficient representation of this may pose a problem. So one solution to this may be to just resample the data so that you're looking at the entirety of your disease population, and then a smaller subset of your healthy population could be a potential solution for some of your research projects. Okay, next I'm going to talk about exploratory data analysis. So the point of exploratory data analysis is because often when you start with machine learning projects, you're starting with exactly what's shown on the left of the screen, a really big CSV or Excel file that has a ton of features across the top, and then a ton of entries, so different patients, different pathology images along the bottom line. And to understand the variance and what's going on in the data is almost impossible from just the tables. You really need to be able to visualize and understand and look at your data to be able to understand it. We'll review dimensionality and data pre-processing here to go over how you might go about this. So the top figure here is a heat map. What the heat map is looking at is features that tend to be highly correlated within the groups. You probably want to drop features of high internal correlation because it's unlikely that you need 10 of those features to feed your machine learning model. You only want to retain those features that are able to provide variability that the model can learn and train based on. The bottom plot is showing PCA, which is principal component analysis. It's a dimensionality reduction technique. So if you're starting with 15,000 or 1,500 features and you're trying to only use the ones that are predictive to reduce overfitting, and secondly, to reduce the data needs of your experiment. These types of dimensionality reduction algorithms may be a useful approach. Okay, moving into dimensionality reduction. What dimensionality reduction does is it takes the high dimensional feature space that you began your project with and seeks to reduce it to the minimum set of features that are necessary to make the kind of regression or classification task necessary for your data. The reason you want to do this is, one, because it's expensive and difficult and time consuming to train models on very large sets of data. Secondly, because if you have high levels of correlated features within your training, it makes it difficult for the model to validate on itself. So if you have a ton of correlated features, your cross-validation steps are more likely to have less close predictive accuracy. Principal component analysis is one example of a technique that can be used for dimensionality reduction. What principal component analysis does is it takes your input data and remaps it in a different high dimensional space to a different representation. Now, importantly, principal component analysis is just moving your data, essentially. It's stretching it in new ways and to make a visualization that is on the axes of most variation. And you can actually see here, if you start with a data set with 40 features, your principal component analysis is actually going to produce 40 different principal components. Now, you might see plots that are most likely represented as component 1 and component 2 or 3, because that's what we can visualize. But the way you achieve dimensionality reduction using these types of algorithms is by dropping components that don't have a high amount of explained variance. So as you can see here, something like 90% of the variance within the data would be explained by the first 30 features or so, meaning that you can probably drop the last 30 and lose almost no predictive value within your data set, and you'll have an easier time training your model, and there'll be more robust fits. Principal component analysis is one example that I'm covering here because it's probably the most easy to wrap your head around. All it's doing is just stretching the data in a way that maximizes the variance along the axis, along the X and Y axis. There are other techniques like the T-SNE and UMAP, which might be useful for your use case. I just wanted to highlight those as well. Okay, moving on for exploratory data analysis. Other steps you may want to do is to add new features and create dummy variables. So here, it's looking at an example that I believe we covered last week, where you're trying to predict the chance of strep in a group of NHL players. Now, for a division category, that's useful for people to look at, but the problem is the model prefers to work with numbers, and you can't perform machine learning predictions on Atlantic versus prediction. One approach to do this may be to separate it out and say that Atlantic is 1 and Pacific is 2. But the problem with these kinds of changes is that the model will try and interpret meaning from the difference between Atlantic and Pacific being a number. The solution to this is to create a dummy variable. So you'd have a category that said Atlantic, and then it would be 1 if it was Atlantic, and then Pacific, same thing, it'd be 1 if it's Pacific, and it would be 0 otherwise. The benefit of this approach is it allows you to have the same input, but you don't run into these problems of interpreting the differences between 1 and 2 in the case of a single column of variables. Secondly, I want to talk about adding new features. So this is the process of feature engineering and data augmentation. So what data augmentation does is it seeks to add new features to your data set that might improve the model's predictive ability. And it can also seek to increase the N by slight modifications that retain the K features. Here, this is what data augmentation might look like for a neural network. It's the same image of the cat, and they're just rotating it and stretching it around to increase the amount of data that goes in. This is useful for machine learning models because if you think about it, you don't want your model to predict cat because it got really used to seeing an eye in this pixel right here and then the mouse right below it. You want it to recognize the shapes and elements of a cat rather than a cat in this exact position. And that's what augmenting your data set in this way would allow it to do. Importantly, you still have to retain the key features. So here, as you can see, most of these images work, and you'd expect the model to be able to guess cat, but except for the last one here, it's kind of ambiguous, and maybe not everyone would look at this image and be able to correctly identify the image as a cat. So that's something you want to keep in mind. You don't want your augmentations to go too far. In terms of more ways to look at data are here. We're looking at a scan, an imaging procedure, and we can see that one feature that might be used is entropy to predict the image. So entropy is a measure of how unexpected the data is, and that would allow the model to train and improve these deeper tissue imaging techniques in a way that a model not exposed to those types of features would be unable to. Last example of feature extraction augmentation is from a pathology paper right here. So you could feed the model a raw pathology image like this, but what these researchers sought to do is they tried to implement their biological understanding of disease into the model. So they built a sub model within theirs that identified epithelial and stromal cells within these samples of tumor cells. And now these individual sub areas of epithelial and stromal cells were analyzed by the model to extract features describing the nucleus of the neighbors of epithelial cells, the morphology of these cells and how they look, the relationships between the two different classes that were introduced, and relationships at the subcellular levels, so between nucleus and cytoplasm. The importance of what I'm trying to demonstrate here is that in the absence of this type of approach, a machine learning model may not be as successful in terms of being able to predict changes and being able to predict the 5-year survival of patients. But when you augment the images through this type of feature extraction and codifying the biological understanding into parameters that the machine learning model can learn on, you're much more likely to improve the prediction. And again, just to highlight, they ended up using logistic regression for their building of models here. It's not something extremely complicated or that uses particularly advanced or unreachable techniques. It's just logistic regression stacked upon this biological understanding and insight that was implemented in the code. Okay, so in summary, you're going to want to try and capture as much data as possible during your acquisition step. And you can always reduce the dimensions or reduce the features later, but it's good to maximize the capture of data because you don't know what might be useful for the model. Secondly, you can use dimensionality reduction approaches to minimize redundant features within your data set and make it more likely that your trainings are going to generalize or be useful outside of your particular training. Feature extraction techniques driven by biological insight can improve your model performance over time and also make it so that models could be more successful at prediction tasks because you're actually translating that human understanding into something that the model might be able to build upon. Lastly, I just want to highlight the model does not need to be too complex in order to be successful. Both of the examples from recent papers I was showing you just use logistic regression, but they use that biological understanding of how disease works and how these parameters might relate to one another to improve the predictive power of the model as opposed to increasing complexity. Question break, and then we're going to jump into the coding session. Are you sharing the notebook?
Yeah, so I'll share in the chat here. I'll take here's a link to the notebook in the chat if you want to follow along. Sorry, my Zoom is bugging out. So what you have to do, first thing you have to do is press File and press Save to Drive, and I'll save a copy of this notebook. There was a submitted question. The question was, how do you use machine learning when your data is survey type data, like a Likert scale, for instance? And Michelle, you can chip in as well. So I'm assuming the main problem with surveys and data is that there's a lot of confounding. For instance, if the survey is asking students how satisfied they are with their education on scale of 1 to 10, different students have different criteria for answering 5 out of 10. So it's not, you won't get the fine, consistent resolution you'll get compared to, let's say, measuring a blood pressure. So the tips are, number one, sometimes you just can't do predictive analysis. Sometimes predictive analysis isn't the goal. And you just want to compute p-values to know what might be significant. You want to compute a Kruskal-Wallis test to see that, hey, there is some significance here that warrants further controlled testing. But if you think your data is really, really good and you want to do predictive analysis, stick to the really simple models like logistic regression, at most a random forest decision tree. Do not use a neural network for survey data because of all the confounders, your neural network will predict something really well, but it's almost guaranteed to be overfit. So those are my 2 tips for survey types of data.
For like a dimensionality reduction, how do you choose what technique you would use, like whether PCA or like the stochastic? Or I'm not sure that's too technical a question.
So I personally usually start with PCA because it's the one I understand the best. I know for genome analysis and like single cell analysis type projects, people prefer TSNE and UMAP. It's kind of just on a field by field basis. I don't know if you have more to add to that, Ricky. No. Okay, great. So I'm going to jump into the coding section. So today, similar to last session, we have a Jupyter notebook prepared for you to run through some of the machine learning workflows that you might use. The first block here is just loading very common Python packages for use in your own research. You can take these notebooks and adapt them to your own projects. That might be something that might be useful for you in the future. It's good to have access to these. So the first cell, I'm just going to hit Shift Enter. Or notebook. Okay, so this is just telling me that the notebook is authored by Google. Anyway. Great, so we've loaded all the packages and we specified some parameters for the notebook to display and render well for us. The next step, we're loading a wine data set into a variable. So that what this is doing is having the data accessible for us to then run analysis on. And I believe it's going to print some features. There we go. Okay, so as you can see, it's a bunch of different types of wine, and it's basic information like its alcohol content, its malic acid content, ash, alkalinity, all those types of stuff. We're going to use this data to perform some machine learning, probably classification tasks as we go on. So to begin, we have unsupervised learning. Again, unsupervised learning is where we're trying to cluster data and learn underlying relationships based on trends that exist within the data itself, rather than underlying class labels. So here, even though we actually know the correct categories of the wine, for now we're excluding them to see if we can develop some understanding of the biological variation that's occurring underneath. And this is a very common approach when you have supervised machine learning approaches and the ability to look at labels in your model. The reason is that it's kind of a relationship between unsupervised and supervised learning. Unsupervised learning will help you understand your data and learn about connections that you previously may not have thought about. And you can use this to pick parameters and pick features that might feed into your model afterwards. So here we're going to start with 2 features. You could change this to be any of the other features. We're just doing the first and second one. Again, Python starts with 0 and increments up. So don't be confused even because it says feature equals 0. Here we're loading the data into a data frame, and we are generating a scatter plot to look at the features. The first plot shows you what the data would look like. Actually, I should just run it. Here we go. So here you can look at the actual column values in your data, but the first plot shows you what it might look like without labels. You can see that there's kind of intermixed. There's no clear class separation for the 2 features I picked here between the various groups of alcohols. But when you look at it with the class labels put on top, you can now separate the data and see that there is some separation. Maybe there's something further, but more likely it's just because I'm looking at 2 features, and perhaps by looking at the rest of the 13 features, you may be able to improve the predictive accuracy of the model. So here we're going to implement a k-means clustering technique to look at our data. This is going to perform clustering, so unsupervised learning, to try and identify groups within the data. Here we're going to say that there's 3 clusters. You just specified a parameter, and then you say how many iterations you're going to go over. This is just some generic blocks of code where you're trying to instantiate the model and then fit it to the particular data that you're inputting. And this last block tries to visualize the data in a way that we can look at the predictions of the model. Okay, so the model now separates data into these few clusters. What we really want to look at is a comparison of this figure, which is ground truth, and this figure, which is the predicted cluster. As you can see, it's pretty close, but there's some underlying mixing of the data that we have in our ground truth labels that the model is not able to predict based on using k-means. Okay, so as opposed to doing k-means on 2 features, we're going to try and do this again on all the features and see if this produces a different result. See, so here we're able to capture a more complex relationship in the data that's not present, where the 2-dimensional separation didn't capture the heterogeneity that was going on in this area. A full dimensional k-means clustering technique is able to separate the data out in a way that the lower dimensional version was not able to do it. So moving on now, rather than looking at k-means, we're going to talk about some dimensionality reduction approaches. Here we'll start with PCA. This is the technique that we covered previously. So what PCA does is it rescales the 13 features that we put in. So things like the alcohol content, the acid content, and it's looking to generate, instead of the pre-existing defined categories, it's looking to generate categories that separate the variance. It's a bit less interpretable, but we can always look at our principal components and see which features end up contributing the most to the variance that is observed. So as you can see here, most of the variance in the data can be explained, I'd say, up till feature 10, we're not really gaining a lot. Each additional feature is really not contributing too much to the explained variance of the data. And you may, because we're only using 13 features, it's really okay, but for a much more higher dimensional data set or feature space, you'd want to cut it off early at say 90% explained variance or something like that, or 85, and go on from there, because the data costs of adding more features really start to blow up. Okay, so this is visualizing the principal components rather than what we visualize up here, which is alcohol and malic acid content. We can see how the principal components separate the data. And again, it's showing the true class labels rather than what we're predicting the class labels to be. As you can see, it's a bit better. We're able to separate out the data into chunks rather than have overlapping sets of the data where it's hard to separate. So that's one benefit of principal component analysis. By really, instead of looking at the underlying features, by separating it out into cases that have the most variance, you're now able to separate your data in a way which may not have been possible otherwise. So here we're printing out the principal components to see the features that are most influential. And there's some text telling you that in this data set, the most predictable feature was flavonoids. So the flavonoid content is what ended up separating the data the most. And it's useful because unlike UMAP or TSNE, which may be a bit harder to interpret, being able to use PCA allows you to do this flip backwards to look at the most influential features. You can also do this for UMAP and TSNE, but it's a bit harder to grasp because there's more influence of the random component in those types of approaches, because like there's stochastic kernels that they use to implement those models. Okay, jumping into, we're now going to do a supervised classification task where we're using logistic regression to predict whether a tumor is cancerous or benign. I'm running this cell to load the data set similar to what we did before. So the model we're going to train is called a logistic regression classifier. Don't be confused by the name. It has regression in it, but it's still a classification model. It's seeking to separate the data into those tumors that are benign and those tumors that are malignant. In this cell, we're importing the important parameters and specifying the iterations of the data. So here, we're just trying to train a classification model on the first few features. This block of code splits the data into train test sets because that's what we want. This block of code reshapes the data to be able to go into the model. This is for visualization. This section here is the training section and some printing statements to make it easy to look at. And down here, we actually visualize the logistic regression model we have. Just going to run it again for you. I've already run this. Trains pretty quickly. So as you can see here, there is a logistic regression model that's fit to these features, where you can have some level of separation, but it's not great. Here it's saying we get about 86% test accuracies reflectively. Importantly, it's test accuracy, not training accuracy, which may be higher, but still 86% is good. It's not great. But this is only with the few input features. I think it's a couple. We can bump it up by inputting all the features and being able to improve our predictive accuracy. Oh, so this block is talking about the interpretability of logistic regression models. So as opposed to other techniques which may be difficult to understand, you can actually use logistic regression techniques to export the odds ratios or odds of tumors being benign. Here you can see it's 1.92 for the first feature being 0, and then for the first feature being 1, this increments it to 0.03 times less likely that the tumor is going to be malignant. So as opposed to other models, logistic regression seems to be more interpretable because it uses speak and data analysis techniques that are more common and interpreted in medicine. Okay, so lastly, we're going to run the model again, but instead of using a smaller feature set, we're going to use a full feature set and look at what the predictive accuracy is going to be. Here we go. Here we're training the model and we're printing out the accuracies. So the training error here is 0.99 and the test error is 0.97. So it's saying that the model is pretty well hit. It's about 99, 98%. Importantly, the test accuracy is always going to be a bit lower than your training accuracy because the model has not seen the data yet. And lastly, we're able to pull out these parameters that explain that can be converted into odds ratios to understand the underlying relationships in your data using logistic regression models. Okay, so I think that's all we have prepared for you today. I hope this was helpful. And if anyone has any questions,